Dear students, in this video you will learn about Blondel diagram, that is constant power circle, and operation of synchronous motor at constant load, variable excitation. First we will see Blondel diagram, that is constant power circle. So it is extension of simple phasor diagram of synchronous motor. So constant power circle diagram is a extension of simple phasor diagram of synchronous motor. In previous video we have seen phasor diagram of synchronous motor. So it is extension. So if you extend the simple phasor diagram of synchronous motor, so we will get the Blondel diagram or constant power circle. So you know that power input to the synchronous motor, so we are denoting with P in. So P in is equal to V phase I phase cos phi. So it is equal to per phase power. So it is not 3 phase power. So synchronous motor is having 3 phases. So per phase power P input is equal to V phase I phase cos phi. The mechanical power developed per phase will be equal to the difference between input power and copper losses per phase of the winding, right. So mechanical power developed by the synchronous motor is equal to P input power minus power consumption due to copper losses in windings per phase. So you can write copper losses per phase is equal to IAPH square RA. So you generally will write I square RA. So in synchronous motor, what we will write, copper losses per phase is equal to IAPH square into RA. So according to the mechanical power developed by the synchronous motor, so according to the statement mechanical power developed, PM is equal to input power minus copper losses. So this is per phase. Okay. For mathematically convenience, let VPH consider as a V and IPH consider as a I. For simple simple simplification, so we are considering VPH is equal to V and IPH is equal to I. So let we substitute V and I in place of VPH and IPH. So we will get mechanical power developed by the synchronous motor, PM is equal to VI cos phi minus I square into RA you will get. Okay. So you simplify this one. So if you simplify, so you will get here I square minus VI cos phi by RA plus PM by RA is equal to 0. So simplify and equating, we will get that one. So now coming to the phasor diagram of synchronous motor. So here is delta is the load angle. So when the load increases, load angle will increases. So and the current drawn from the supply will be increases, but speed remains constant in synchronous motor. So due to that concept, from the equation in previous equation, so here we can write and we can draw the phasor diagram of synchronous motor. So this is the phasor diagram. First figure shows the phasor diagram and the second figure shows the Blondel diagram. So here, so we are changing the angle. So angle theta with respect to the OA line. So you can get circle of constant power. So circle of constant power you can get, and theta and pi you will get, power factor angle and load angle you will get it from the Blondel diagram. So now we will move to the operation of synchronous motor at constant load and variable excitation. So excitation is main important for synchronous motor. So without excitation, synchronous motor will not run. So excitation will be in the form of DC supply. So here, so we have seen previously when the load changes for constant excitation, current drawn from the motor, current drawn from the supply by the motor is increases, right. So, there is no changes in the speed, but in excitation, that is field current is changed, keep the load is constant. The synchronous motor reacts by changing the power factor of operation. So, here pi value will be changes. Okay. So, most interesting part of the synchronous motor is, so we are changing the load, and we are keeping the speed is constant. So, but in other type of motors like DC shunt motor and DC compound motors and even induction motor, when the load is changes, when the load is increased, the speed will be decrease, right. But here the speed should be constant. So, consider this motor is operating at constant load, the corresponding load angle delta. So, at start consider normal behavior of synchronous motor, where the excitation is adjustable and get back EMF EB is equal to V. So, that is equal to supply voltage. So, induced EMF is equal to applied voltage or supply voltage. Such an excitation is called normal excitation of the motor. So, when the back EMF and supply voltage both are equal, then excitation is called normal excitation of the motor. Okay. So, here the motor is drawn certain amount of current from the supply and power input to the motor is SP input. The motor power factor is lagging in nature, since due to the windings, inductive windings, the power factor will be in lagging nature. Okay. So, why it is lagging nature is, so due to windings. So, windings are behaves like inductive, so power factor will be lagging. Now, when the excitation is changed, if you change, so there is a chances of changes in the losses of the motor. So, we will get losses will be changes. Now, power input also remains same for constant load. So, demanding same power output, that is P input is equal to root 3 into VL IL cos pi, that is equal to 3 into VPH IPH cos pi in terms of phase voltage and phase current. The most of the times for the synchronous motor, the applied voltage will be constant. So, hence we are getting constant input power to the motor. The VPH phase voltage is constant, then IPH into cos pi will also remains constant. So, here we have one important note. So far this is entire operation of variable excitation. It is necessary to remember, that is the cosine component of armature current IA cos pi remains constant. So, motor adjust its cos pi, that is power factor nature, and value, so that IA cos pi remains constant. So, here power factor is adjust, then the value of IA cos pi will be remains constant. So, when the excitation of the motor is changed by keeping the load constant, so excitation if you change, the magnetic flux inside the motor will be increase or decrease. So, based on the excitation. So, this reason why the motor is synchronous motor reacts by changing in power factor to variable excitation conditions. So, by changing the excitation, so we are keeping IA cos pi is constant. Okay. So, without changes in speed, without changes in the load, so we are changing the excitation. So, by that power factor of the synchronous motor will be changes. See, this is about bundle diagram and variable excitation of synchronous motor. So, in next video we will see under excitation, over excitation and critical excitation. Okay, thank you everyone.